Welcome to the fundamental bridge between reality and data, the distinction between the parameter, beta, and the statistic, beta hat. In the world of science and economics, we rarely know the absolute truth. We only have estimates. Today, we will learn how to distinguish the true value from our best guess. Section 1. The population and the parameter, beta. Imagine the entire world as a set of data points. A parameter is a fixed numerical value that describes a characteristic of an entire population. In a linear model, beta represents the true relationship between variables. For example, if we could measure every single human being, the true effect of education on wages would be our beta. It is often denoted by Greek letters because, like the Platonic ideal, it is perfect but often invisible to us. Section 2. The sample and the statistic, beta hat. Since we cannot interview 8 billion people, we take a sample. A statistic, or estimator, denoted as beta hat, read as beta hat, is a numerical value calculated from this sample. While beta is a constant, beta hat is a random variable. Why? Because if you take a different sample tomorrow, your beta hat will change. The hat is the symbol of estimation. It is our humble attempt to wear the crown of the true parameter. Section 3. The OLS intuition. How do we get from dots on a screen to a specific beta hat? We use methods like ordinary least squares, OLS. OLS tries to draw a line that minimizes the sum of squared vertical distances between the observed data and the line. Mathematically, beta hat equals x transpose x inverse x transpose y. This formula is the engine that transforms raw data into an estimate that hopefully points toward the truth. Section 4. Sampling error and the distribution. Because beta hat depends on the sample, it has its own probability distribution. This is the sampling distribution. According to the central limit theorem, under certain conditions, our estimates will follow a normal distribution centered around the true beta. The spread of this distribution is the standard error. A smaller spread means our estimate is more likely to be close to the true value. Section 5. Properties of a good estimator, blue. Not all estimates are created equal. We look for estimators that are unbiased, meaning that on average, E of beta hat equals beta. We also want them to be consistent, meaning that as our sample size grows toward infinity, our estimate collapses exactly onto the true parameter. The Gauss-Markov theorem tells us that under certain assumptions, OLS is the best linear unbiased estimator, blue. Section 6. Inference and confidence intervals. Since we know beta hat isn't perfect, we report it with a confidence interval. We might say, we are 95% confident that the true beta lies between these two bounds. If our beta hat is far enough from zero, we say it is statistically significant, meaning the relationship we found is unlikely to be due to mere chance. In conclusion, beta is the hidden law of nature, and beta hat is our window into it. Understanding the gap between them, the sampling error, is what separates a casual observer from a rigorous data scientist. References: Gujarati, D.N., Basic Economics; Woodridge, J.N., Introductory Econometrics, A Modern Approach; John E. Friend, Mathematical Statistics.